Okay, so this is the fourth lecture out of chapter 3. So in this lecture, we cover this concept of stoichiometry. So for most people, students in general chemistry, this is the hardest material for them to wrap their minds around. So it's really not that difficult once you understand the concept, but getting to that point of where you understand the concept can be a struggle for students. So definitely recommend you pay very close attention to this video. Read the book, watch other videos on it until you wrap your mind around this. Once you wrap your mind around it, it's pretty easy, and you need this material in order to understand other concepts in this semester. Okay, so stoichiometry is basically just the calculations used to determine how much of reagents go into a reaction and calculating how much product should come out of a reaction. So the math is simple. Yeah, again, it's probably the hardest topic for students in Gen Chem 1 to grasp. So we're going to introduce the topic using a much more simple analogy. So how to make the perfect sandwich, and how to make a lot of them. So not just one sandwich, but maybe you want to make sandwiches for a party or something, right? Okay, so we got some bread. What kind of bread? So maybe this is wheat or rye bread. What kind of cheese? Well, it's got holes in it, so this is going to be Swiss cheese that we're using to try to distinguish between everything. And so we're going to need to put some meat on this sandwich. So sorry if you're a vegetarian, but I guess this could be a vegetarian meat. That would be fine. So what kind of meat do we want to use? So what would go with rye and Swiss, or wheat and Swiss, maybe ham, maybe turkey? So let's call it turkey, or maybe it's a vegetarian. And we're going to make a sandwich. So our sandwich has to have 2 pieces of bread, has to have 1 piece of cheese, and it has to have 3 slices of meat on it, okay? Okay, so we're going to go through 4 different scenarios. So the first scenario, I tell you how much of each ingredient you have. So these are the ingredients on the left of the arrow. So that's what in chemistry we would call the reagents, right? So I tell you how much of each you start with. You tell me how many sandwiches you can make. And the sandwiches, of course, would be our product in this case. So if you tell me how many sandwiches you can make, you're basically telling me the theoretical yield of this reaction. So we can probably all do the math, right? It's pretty simple math. If you have 20 slices of bread and there's 2 slices of bread per sandwich, then how many sandwiches could you make? Well, this would allow you to make 10 sandwiches, right? And you have 10 slices of cheese. There's 1 slice of cheese per sandwich, so that would allow you to make 10 sandwiches. And each sandwich has 3 slices of meat, and there's 30 slices to begin with, so that would allow you to make 10 sandwiches. So 10 is our theoretical yield. So if you can do that, you just did stoichiometry. So if this was a chemical equation, then this would look like we need 2 of these and 1 of these and 3 of these to make 1 of those, right? So those coefficients are ratios, and it always has to be in this ratio. It has to be a 2 to 1 to 3 to 1 ratio to make this particular sandwich. Okay, so scenario number 2. So instead of I telling you how much ingredients you have, what the reagents are, I tell you how many sandwiches I want you to make. So I want to make 8 sandwiches. So now we're just simply going to work backwards, okay? If I tell you how much product to make, then you can tell me how much reagent goes into the reaction, right? So how many slices of bread would you need? Well, you would need twice as many slices of bread, right? You would need 16. How many slices of cheese? You would need 8. And how many slices of meat? So 3 per sandwich, so that would be 8 times 3. You would need 24, right? So now you just did stoichiometry working backwards. Okay, so third scenario, and this is getting closer to reality. So in reality, most reactions are not perfect. You usually do not get the maximum amount that you could get. So you usually do not get the theoretical yield. So in this case, I'll tell you how much ingredients you start with, and I'll tell you how many sandwiches you actually made. which is not the theoretical amount. So in this case, you're going to start with 20 slices of bread, 10 slices of cheese, 30 slices of meat. We showed here that you can make 10 sandwiches, but what if we only made 6 sandwiches? So we did not get 100% yield. So then I could ask you, well, what is the percent yield? And the percent yield is just the actual yield divided by the theoretical yield. So the actual yield is 6. The theoretical yield is 10 times 100%. So the percent yield of this reaction would have been 60%. Okay, so then I could ask you, so how much of each ingredient is left over? If you don't get 100% yield, then you must, so if you don't get 100% yield, then one of a couple of things has happened. Either a side reaction has happened and you made something else, and some of your starting materials got diverted into making something else. And if that did not happen, then if there are no side reactions is what we would call it, then if there's no side reactions, then you must have some stuff left over, right? You must have some bread, meat, and cheese left over. So how much is left over? So that would be another stoichiometry question. So if you only got a 60% yield, well, we can do the math here pretty easy. If you made 6 sandwiches, then how many slices of bread did you use? Well, you must have used 10 or 12, right? So how many is left over? 8. If you started with 10 slices of cheese, then you use 6, and there would be 4 left over, right? And 6 times 3 would be 18 slices of meat left or used, and so you would have 12 left over, right? So if you wanted to do this mathematically, what you could do is, well, you started with 20 slices of bread, for example, and the yield was 60%, so we could convert that back to a fraction, so divide by 100, so 0.6. So 20 times 0.6 is equal to 12, right? So this is the yield. So if we multiply that by what we started with, and we get how much we used, and then if we wanted to know how much was remaining, then we could take the 40%, which is what would be unreacted. So 20 times 0.4 would give you 8, right? So we could do the same for the cheese. 10 slices of cheese times 0.6, you use 6. 10 slices of cheese times 0.4, there's 4 left over. And you would do the same with the meat as well, right? Okay, so now the fourth possible scenario, which will be the most complicated that we'll see, would be, in this case, you do not have the correct amount of each ingredient. So you go to your cabinets and get your bread, and you go to the fridge and get your meat and cheese, and you realize you do not have the right amount of each one to make sandwiches. So you can make some sandwiches, but you can't use all of the ingredients. Some are going to be left over, but one of them is going to run out. You're going to run out of. So in these scenarios, you had exactly the right amount of bread and meat and cheese, right? 20 slices of bread needs 10 slices of cheese, needs 30 slices of meat. But in this case, so it has to be in a 2 to 1 to 3 ratio. So in this case, you don't have that ratio, right? So if you start with 16 slices of bread, 7 slices of cheese, and 27 slices of meat, you do not have a 1 to 2 to 3, or 2 to 1 to 3 ratio. So one of these you do not have enough of, and you're going to run out of it before you run out of the others. So that would be what's called the limiting reagents. So which ingredient will you run out of first? That's what's called the limiting reagent. So which one are you going to run out of first? You start making sandwiches. Which one would you run out of first? Well, if you had 16 slices of bread, how many sandwiches could you make? You could make 8, right? So you could use, if you had 7 slices of cheese, how many sandwiches could you make? You could make 7. And if you had 27 slices of meat, how many sandwiches could you make? Since each sandwich has 3, you could make 9. So bread says you can make 8, cheese says you can make 7, meat says you can make 9. So how many can you make? You can make 7, right? So this would be your limiting reagent. That's the one you're going to run out of first. So your theoretical yield is 7, right? And that's determined based on your limiting reagent, the cheese. Okay, so what if you only actually made 5? So we could calculate the percent yield. So the percent yield, so the limiting reagent is the cheese. The percent yield would be 5 divided by 7 times 100%, which would be 71.4% yield. Okay, so now the harder part here is calculating how much of everything is left over. For the cheese, that is easy because it's the limiting reagent, and the percent yield applies to the limiting reagent. So, of course, you can just visually figure this out, right? You had 7 slices of cheese and you made 5 sandwiches, so you use 5 slices of cheese and there's 2 left over. But you could do this mathematically as well. Did I do that down here? Yes. So if you start with 7 slices of cheese times the percent yield, 0.714, if you convert that back to decimal form, you use 5 slices of cheese. Start with 7 slices of cheese. Now if you take 100% minus 71.4%, you get 28.6%. And if we convert that back to decimal form, 0.286, so 7 times 0.286, there's 2 slices of cheese left over, right? But this calculation does not work for the reagents that are in excess. So the bread is in excess, right? You're going to have some bread left over and you're going to have some meat left over. The percent yield does not apply to them. So it's easy to see, just do the math. If you started with 16 slices of bread and you multiply it times the yield, that would say you used 11.4 slices of bread, but that's obviously not true. If you made 5 sandwiches, you used 10 slices of bread, right? And there's not 4 point slices that's going to be remaining. If you had 16 and you use 10, you're going to have 6 remaining. So the percent yield does not apply to the reagents that are in excess. So what the percent yield does apply to is the quantity of the reagents that are in excess that could have been used. So if you were going to make 5 sandwiches, then that would be 10 slices of bread. Let's see. No, you had 7 slices of cheese. So you could have made 7 sandwiches. That would be 14 slices of bread, right? So you could have used 14 slices. You actually used 10. And you were never going to use 2 to begin with because that was an excess to begin with. And same with the meat. So you actually used 15 slices, right? If you were going to make 7 sandwiches, you could have made 20. You could have used 21 slices. So you had 6 slices of meat that you were never going to use no matter what, because you can only put 3 on a sandwich and you have excess to begin with. So in terms of the math, if you wanted to work out the math, so you could, if you made the maximum number of sandwiches 7, the theoretical yield 100%, you could have used 14 slices of bread, so that times 0.714, that means there would be 10 slices left over. But how many remains? This still doesn't work because you started with 14, and so if you multiply that by the 0.286, that says 4 slices should remain, but that's not true, right? 4 slices remain out of what could have been used. Right, so that would be, well, I got this down here. So you could have used 14, you actually used 10, so if you take the difference there, that is 4, but there are 2 slices that you were never going to use to begin with, so if you add those together, then that would be 6. So the 2, so you would have to add the excess that was there to begin with to get the actual number of what is going to remain of the reagents that are in excess. So hopefully that makes sense. And so we'll apply it to an actual example here in a minute. So what if I gave you this scenario like this? What if I told you you had 21.3 grams of bread, 16.5 grams of cheese, and 32.5 grams of meat? Now how many sandwiches can you make? Well, that's a lot harder, right? How would you answer that question? What would you need to know? Because you don't have enough information to answer that question. What would you need to know to figure this out? Well, you would need to know you would need to know how much each weighs. How much does a slice of bread weigh? Because then you could figure out how many slices of bread you had based on the mass and how much it weighs. Same for the cheese and the meat. You would need to know how much each weighs, and then you could figure out how many each you have, and then you could figure out how many sandwiches you could make. Okay, so let's take a generic chemistry example. So A, B, C, and D would be chemical compounds. So if you have A plus 2B, so that would be your reagents. So we can calculate how much of these we need to make C and D. So you make 3C and 1D for every reaction. So we could calculate how much of those we could make. Okay, so for this equation, so there's a 1 here, right, in front of the A, and a 1 there in front of the D. They're just not shown. So, and a 2 and 3 in front of the B and C. So these coefficients have meaning. So they're a number of things. They're a quantity, not a mass. So we could write this, for example, 1 molecule of A reacts with 2 molecules of B to make 3 molecules of C and 1 molecule of D. So that is a quantity. That is not a mass. That is how many of, just like with the sandwiches, right? You need to know how many of everything that you have in order to figure out how many sandwiches you could make. 16, 7, 27, and you could make 7. So these coefficients are quantities. They tell you the ratio of things. So it could be, or it could be 1 dozen. You have 1 dozen of these, needs 2 dozen of those, and you would make 3 dozen C's and 1 dozen D's. Of course, chemists typically don't count things by ones or dozens, right? Because atoms are really, really tiny. So we typically count things by the mole. So this could also mean 1 mole of A reacts with 2 moles of B to make 3 moles of C and 1 mole of D. And how much is a mole, if you remember? 1 mole of anything is 6.022 times 10 to the 23rd. So these coefficients in front of the chemicals are ratios, they're quantities. And just whatever unit you want to put behind that quantity is fine, so long as it tells you a number of things, not a mass. You could not say 1 gram of A reacts with 2 grams of B to make 3 grams of C and 1 gram of D. That is totally wrong, right? It's not a mass. The only situation that would be true is if A, B, C, and D had exactly the same molar mass. Otherwise, it doesn't work. Okay. So given this equation, then let's scale it. So what if you had 3 moles of A? So if you had 3 moles of A, then I could ask how many moles of B do you need? So it always has to be in a 1:2 ratio. So if you had 3 of these, then you would need 3 times 2, you would need 6 of these, right? If you had 2 of A's, you would need 4 of B's. How much C could you make? Well, it always has to be in a 1:3 ratio. So if you have 1 of A, you can make 3 of C. So if you have 3 of A, then you can make 9 of C. And A and D have to be in a 1:1 ratio. So if you have 3 of A, then you're going to make 3 of D, right? So those ratios always have to stay the same. And again, this could be individual molecules, 1 molecule of A, 2 molecules of B, or 3 molecules of A needs 6 molecules of B, or it could be moles, right? 1 mole of A needs 2 moles of B, or 3 moles of A needs 6 moles of B. Okay, so what if you wanted to make 6 moles of C? So if you wanted to make 6 of this, then how many of A and B do you need? Well, you would need, you would have to take that and divide that by 3, so you would need 2 of A, right? And how much of B do you need? Okay, so if we have 3 moles of 6, so if this is 6, then this has to be 4, right? You would need 4 of B. And then how many D's could you make? Well, this has to be in a 3:1 ratio. So if we double 3, then we have to double that as well. So that would be 2. You could make 2 of D. Okay, well, what if you had 4? What if you had 4 of these, 4 moles of these, and 10 moles of these? Then now you don't have the right ratio, right? So now one of these is going to be a limiting reagent. So which one is going to be limiting? So if you had 4 of these, then you need, it's a 1:2 ratio, then you need 8 B's. And if you had 10 of these, then you need 5 of those, right? Because it's a 2:1 ratio. So 4 A's need 8 B's. You have more than 8 B's, you have 10 of them, so that means B is an excess, so A would be a limiting reagent. Or if you have 10 of these, you only need 5 of these, 5 A's, but you have, let's see, let me get my logic right here. Yes, so if you had 10 B's, then you would need 5 A's, but you don't have 5 A's, you only have 4 A's, so A is limiting, right? So you're going to run out of A before you run out of B. How many C could be made? Well, you use the limiting reagent to figure out C. So now it doesn't matter that you had 10 B's because you're going to do the math based on the limiting reagent, 4 A's. So if you had 4A and A to C has to be in a 1 to 3 ratio, then 1A would make 3 C's, so 4 A's would make 12 C's, right? 12 moles of C. Okay, so hopefully that made sense. And then A and D has to be in a 1 to 1 ratio, so if you had 4 moles of A, you could make 4 moles of D. Okay, and then again, if you were given, instead of moles, if you were given grams, so 6 grams of A, 10 grams of B, how many grams of C and D could you make? Well, you don't have enough information to solve that problem. What would you need? You would need molar masses. Okay, so that's basic stoichiometry, and so now let's apply it to a real example. So if we had this problem, C5H10 plus O2 and reacts to make CO2 in water. So given this, and you had 17.3 grams of this. So given this information, so typical questions that you would be asked would be, how much O2 in grams do you need to react with this much C5H10? How much CO2 in grams can be produced? How much H2O, how much product can you make in grams? And if the reaction actually produces 32.1 gram, what's the percent yield? And then based on that percent yield, if it's not 100% and there's no side reactions, there must be some starting material left over, so how much is left over? Okay, so let's answer those questions. So if you can do this, then you can, if you can answer these 5 questions, then you understand about 75% of everything that you need to know about stoichiometry. And in the next lecture, we'll work another problem that's a little bit more complex to give you the rest, the other 25%. Okay, so where to start? First of all, you have to make sure the equation is balanced. So we have 5C on the left, so we need 5 C's on the right, so we'll put a 5 there. We have 10 hydrogens on the left, so we need 10 hydrogens on the right, so we're going to put a 5 there. Now there's 5 carbons and 10 hydrogens on both sides. And now we need to balance the oxygens, so this is 10 oxygens, and this is 5 more oxygens, so that's 15 oxygens. So we need 15 oxygens on the left. One way to do this, to start this, is let's say we had 15 halves, and then that would cancel, so that would be 15 oxygens, right? But usually you don't use fractions as coefficients, so we can get rid of the fraction by multiplying everything by 2. So if we had 2 of these, so 2 of these, and then 2 of these, so that would cancel the 2's here, so 15 of those. 2 of these will make 10 of those, and 2 of these would make 10 of those. So now that would balance the equation. So 2 of these, 15 of those, 10 of these, and 10 of these. So that gives us 10 carbons on the left, 10 on the right, 20 hydrogens on the left, 20 on the right, 30 oxygens on the left, and 30 oxygens on the right. Okay, so first we balance the equation. Now we convert, now we're going to need molar masses of everything because we're going to need to convert grams to moles. So if we calculate the molar mass of everything, so I've done them for you here, so C5H10, so we use our periodic table, right? And calculate the molar mass of C5H10 of O2, CO2, and water. And then we're going to convert grams to moles. So we're going to convert the 17.3 grams to moles. So if you remember how to do that, so 17.3 grams, so we're going to use the molar mass here, which is in grams per mole. So we have grams on top, so we need grams on bottom. So the 70.13 grams of C5H10 has to go there, and the 1 mole C5H10 has to go there. And then multiply the tops, divide by the bottoms, and that would give you 0.2467 moles of C5H10. Okay, so now what we want to do is, now that we know how many moles of, let's call this A we have, how many moles of B do we need? And if you remember when we did that, we looked at the molar ratio. So now we're going to use molar ratios to convert from moles of C5H10 to moles of O2. So 0.2467 moles of C5H10, and the molar ratio is 15 to 2. So 15 moles of O2 to 2 moles of C5H10. And that would give you 1.85 moles of O2. Okay, so now we're going to convert back to grams. So use the molar mass of O2 that we calculated here. So 1.85 moles of O2, there's 32 grams of O2 in every 1 mole of O2. So that would give you, so you need 59.2 grams of O2 for this reaction. Okay, so now we've calculated how much O2 we need. Now we can calculate by the same process how much CO2 and H2O you can make. So that's going to be our theoretical yield. We're going to calculate our theoretical yield of each. So we're just going to use molar ratios again. Anytime we're going from one chemical to another chemical, we use molar ratios. So now we're going to go from C5H10 to O2 to CO2 or an H2O. So it's going to be a 2 to 10 ratio. Okay, so 10 moles of CO2 and 2 moles of C5H10 will give you 1.235 moles of CO2 can be produced. That's your theoretical yield. And the same for water. All right, so your moles of C5H10 cancel. And so that would give you, that doesn't, yeah. So 1.235 moles of water is your theoretical yield. And now convert those back to grams. How do you convert them back to grams? You use the molar masses that we calculated here. So 44.01 grams of CO2 for 1 mole of CO2 and 18.02 grams of water per 1 mole of water. So moles of water cancel, moles of CO2 cancel, and now you're left with grams. So your theoretical yield is 54.4 grams of CO2 and 22.2 grams of water. Okay, so that's basically what you would expect if this reaction was perfect. You put 17.3 grams of this in, 59.2 grams of that in. You should get 54.4 grams of this and 22.2 grams of that. And there's an easy way to check yourself to see if you did the mass right, because of this concept of conservation of mass, right? Whatever you put into a reaction has to come out. So we can add those two masses together. So we put 76.5 grams into the reaction, and then we can add up what comes out. So the 54.4 and 22.2 grams of water, if we add those together, we get 76.6 grams. It's not quite exact. Why isn't it exact? Because we rounded in this calculations. When we calculated the moles of CO2 and water in the grams, we rounded them. If we didn't round, then they would be exact. So whatever goes into reaction has to come out. Okay, so we answered that. How much O2 do you need? We answered that. How much CO2 you can make? We answered that. How much water can you make? So now what if the reaction only actually gave 32.1 grams of CO2? We just calculated that you could make 54.4 grams, so we can calculate a percent yield. So if you only made 32.1 grams, then you didn't get 100% yield. So what is the percent yield? So we take the actual yield divided by the theoretical yield times 100%. So that reaction would have gone in 59% yield if you made 32.1 grams in this reaction, right? And again, most reactions are not perfect. Most reactions do not give 100% yield. So is 59% yield good? Well, it's all relative, right? So if this was a reaction in a pharmaceutical industry, for example, and that was a pharmaceutical agent, maybe the next best antibiotic, Would a 59% yield be good? Well, that depends. If you're the only one in the world that can make it, then that's a pretty good yield, right? But if there's another company that can make it in 75% yield, then your 59% yield is no good unless your starting materials were cheaper than theirs were, right? So it's all relative, right? If nobody else can make it, then the fact that you can make any is pretty good. But obviously, we would like to maximize that yield out as close to 100% as possible in order to minimize the waste. There's less environmental aspects to deal with then, less waste to deal with, less purification that you have to do, which means less money that has to be spent. And there's more product to sell if you can maximize the yield. Okay, so last question then. So since we did not get 100% yield, then assuming there's no side products, then how much starting material is left over? So the math here is pretty easy because we had exactly the right amount of everything, so the percent yield applies to both the C5H10 and the O2. So 17.3 grams started with times 0.59. 17.3 times 0.59. That means 10.2 grams reacted. So 17.3 minus 10.2 equals, so that means there would be 7.09 grams left over. Or of course you could have done the 100% minus 59% to give you 41%, and then 17.3 grams times the 0.41, and obviously you get the same number. So if the reaction only went in 59% yield, there would be 7.09 or 7.1 grams of C5H10 left over, and there would be some O2 left over. And at the end of the reaction, you would have to do a purification to separate everything, which is another big part of chemistry, is separating things to get pure material out of everything. Okay, so that's a basic stoichiometry problem. Hopefully that made sense. It's a lot of work, a lot of steps involved, but the math is simple. You just have to know how to work through each of the steps. And then in the next lecture, we'll take one more example of this. Okay, so we will stop there.